In its natural state, a wire carries no current and has no effect on a nearby compass. However, Hans Christian Ørsted discovered that moving charges create a magnetic field. When an electric current flows through the conductor, it generates a magnetic field. Notice how the compass needle instantly reacts to the flow of electrons. To determine the direction of this field, we use the right-hand rule. Point your thumb in the direction of the current, and your fingers will curl in the direction of the magnetic field lines. If we look at the wire from above, the magnetic field forms perfect concentric circles. These lines never intersect and are strongest closest to the wire. The strength of the magnetic field, denoted as B, is inversely proportional to the distance from the wire. As you move further away, the magnetic force weakens rapidly. The field strength is also directly proportional to the amount of current. Increasing the amperage creates a denser, more powerful magnetic field around the conductor. We calculate the exact magnitude of the field using this formula. The constant μ0 represents how easily the magnetic field passes through a vacuum. If we flip the battery and reverse the current direction, the magnetic field also reverses its orientation. The right-hand rule still applies, simply point your thumb downward. By bending the wire into a coil, or solenoid, the magnetic fields of each loop add together. This concentrates the field through the center of the coil. Adding an iron core creates an electromagnet. The core amplifies the field, creating a temporary magnet that can be turned on and off with the current. This principle is the foundation of modern technology. From the motors that drive our appliances to the speakers that produce sound, current-carrying conductors are everywhere. In summary, every electric current creates a magnetic field. By controlling the current and wire geometry, we can harness magnetism for countless applications. Generated by Vision Solve AI.